Okay. Okay. So far, what we discussed is analog, right? So we first discussed analog modulation, also analog demodulation. We also looked at what it would be the system performance when you have a noise, right? So simply speaking, when you have a noise in the channel, you always want to measure the SNR. Okay, signal power divided by noise power, SNR. SNR is the metric that you always use in order to measure the bit error rate and also the performance. Okay, so that's the whole story of analog. From today and onwards, we are going to discuss the digital signals, right? Okay, we're going to look at the digital signals. So look at the analog and how to transit from analog to digital. What we're going to discuss first of all is the analog digital processor, also compared with the digital signal processor. So here is the example. Here's the analog signal processing. So maybe this is like 50 years ago or somewhere long back. When you have analog input signals and you do analog signal processor, this is an analog hardware. Now you do analog output. For example, you have a voice. Our voice is analog. You do some processing, and you're going to have an analog output. So that's typically what happened long ago. But now, these days, what we're going to use always is the digital signals, right? Digital signal processing. So what you're going to do is, originally it is analog, and eventually it's going back to analog, right? Our voice and every signal you see in daily life is analog signals. So we always start from analog. So that's going to be input to your system, but your system is a digital signal, digital systems with the digital signal processor. So what to do is that original signal is analog. So first thing to do is A to D converter, analog to digital converter. So you would convert analog signals to digital signals. Okay? And then you run the digital signal processor. And after that, your output is still digital. Okay? Put that digital signal into the digital to analog converter, going back to analog. So it looks like this is more complex, right? Because you change analog to digital, do processing in digital, and then again going back to analog. Looks like this is more complex. Okay? From the block diagram perspective, looks like this is more complex. But in fact, this one is using the digital signal processor. So this one is much better in many different ways. This is much better in terms of error. Especially when you have an error, this is much better. And also this is much cheaper, much cost efficient. So we always use this kind of technique. We never use this, right? We are always going to use this. So to use this kind of technique, we need to learn what is the AD converter and what is the DA converter. Okay? This part, digital signal processor, you are learning from DSP course. Right? DSP course is to learn this part, also this part, right? But we're going to review a little bit on this part, A to D converter. So here is the advantages of digital signal processing. First of all, you are using microprocessor in DSP. Okay? So using the microprocessor, you're using very easy and stable processing. Second thing is your result will be stored in the memory. You're going to use a digital memory, okay, without deterioration, which means that your value is not going to be changed. Once you put the value in the memory, that value stays there. Okay? That value stays there until you remove it. Right? That's what that means is without deterioration. Okay? So the value can be easily stored in the memory. Lower cost because of a VLSI technology. Right? So your hardware is very cheap. Especially for digital hardware, it's very cheap. So it's very cost efficient. And efficient resource management, something like this. We're going to talk about this one a little bit later. But when you look at the signal in digital, you can always use some technique like this. Compression. You know compression, right? Zip, like in computer, zip, right? Compressing. So that's always possible in digital form. Also the data management, coding. We're going to look at some of these things later. But this is actually also very important. We do some processing to do compression, to do coding. All these things is possible when you have a digital inputs. We also have a limit of digital signal processing. Because here, when you convert the analog signal to digital signals, now inside here, you are doing sampling. Okay, we're going to look at that in the next slide. But this is a hardware. This is also hardware. Every hardware needs a clock, right? Digital circuit needs a clock, right? Digital clock. And you cannot increase the digital clock to like 100 gigahertz. Okay, your hardware always has a limit. Your clock maybe can be maybe 1 gigahertz or something like that, right? So your operation is limited by the clock. There is a certain limitation. But still, this digital signal processing is much, much better than analog signal processing. That's why we use digital signal processing all the time. Okay, so going back to the basic, what we need to discuss is some of the signal types. First, in general, there are many different types of signals. Continuous time signal, discrete time signals. We also have a continuous value, discrete value. So the time domain, continuous time, discrete time. On the value, continuous value, discrete value. Okay, we'll look at that in the next slide. There are also deterministic signals and random signals. What is the deterministic signals? Deterministic signals is something like you can expect what is coming later because it is already deterministic, right? You can expect because the signal is already fixed, already determined. However, random signals is completely random. You cannot expect. You never know what is coming, right? Because it's random. So deterministic is like based on the past and present, the future values can be expected. It's all known. I know everything about the deterministic signals, right? Every single value, you know everything. So that's deterministic. Random is completely random, like a noise, right? You never expect, you never know what is going to be exact value. In noise, such kind of thing is random. There are also periodic signals, aperiodic signals. Aperiodic means there's no period. Okay, it's not repetitive. It doesn't repeat. So for example, the graph on the left, this is a periodic signals. You see that signal is repeat, right? Signal repeats here, here, here with a period t. Okay, same thing repeats again and again. But this is aperiodic. Okay, there's no periodicity. It just goes like random. Okay, continuing the classification of signals. This picture on the left up here, on the left top, this is a continuous time. See here, this is a time domain. Continuous time and also continuous value. On the y-axis, this is a value. This is time, x is time, y is a value. See that continuous time, continuous value. This is what we call as analog signals. Okay? Every analog signal we see has a continuous time, continuous value. So this is the real signal. Real signal in practice. Everyday life, you see this. Our voice, something like this, right? Like an electromagnetic wave with a certain frequency. Or your cell phone transmits a signal to the base station. That's also something like this, right? Analog signals. Eventually, it's going to be analog signals, waveform over the air, right? That's what it looks like. These analog signals go into the A to D converter and eventually become digital signals. And this is what digital signal looks like. And digital signals have discrete time, discrete value. So analog has continuous time, continuous value. Digital signals, discrete time, discrete value. But you cannot change this one to this right away. Okay? How to convert analog to digital? You need to have two different processes. One is sampling, Second is quantization. We have two different two different processings inside the A to D converter. Okay? Inside the A to D converter, first thing to do is a sampling. What happens when you do sampling is that continuous time now change to discrete time. That's sampling. When you do sampling, you have a sampling frequency, right? For example, like 1,000 hertz. That means you are sampling 1,000 times per second. Okay, so sample duration in that case is going to be 1 millisecond because you sample 1,000 samples within 1 second. So sample duration is going to be 1 millisecond. Okay, so that's what happens. So when you sample this, when you do sampling of these analog signals, you get discrete time sample. Okay, time is going to be now discrete based on your sampling frequency. However, look at the value here. That value can be still continuous value. So how to change the continuous value to discrete value is to use a quantization. Okay, quantization. So what the quantization means is that your value cannot be any value, like analog continuous value. Your value has to be discrete value. So your value is going to be either this one or this one, this one, this one, this one. You can never have a value in between here. This value, your output, you're never going to have this value. Your value should be here or here or here, 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 one of these. Okay, so that's the quantization. So eventually, when you apply the sampling, quantization, this signal now changes to this signal. Sampling, the important thing is sampling frequency. Okay, based on certain sampling frequency, you change this into discrete value, discrete time. Based on the quantization, you're changing continuous value into discrete value. So based on these two processes, eventually this one becomes the discrete value, discrete time, discrete value. So this is our digital signals. Okay? So for sampling, as I said, what you need to decide is sampling frequency. For quantization, what you need to decide is the number of bits for quantization. Right? Number of bits. So for example, right? Let's look at the sampling first. If you do a sampling, 1 kilohertz, or if you're sampling 2 kilohertz, what's the difference? If you take 1 kilohertz of sampling, your sample duration is 1 millisecond. But if you take a 2 kilohertz of sampling, the sample duration is 0.5 millisecond, right? So you sample it more finer, okay, finer samples. That's what you do in sampling. So generally, if you sample with a high sampling frequency, that's generally better. But if you increase the sampling frequency, what's the problem? Your sampling frequency is too fast. Then what's the problem? Complexity. It's too complex. Okay, complexity is very high. That's not good, right? But if you sample it too slow, what's the problem? Complexity is low, but there is a problem, right? What's the problem? You lose information. Or in other words, what is the word that you typically aliasing problem? Aliasing. So if you sample it too slow, you're going to have aliasing problem. Okay, we'll see that in the next slide. So that's what happened in the sampling. So you need to choose a sampling frequency very carefully. Okay, not to increase the sampling frequency too high, because if you choose a too high frequency, sampling frequency, complexity is too high. Okay. However, if you choose the sampling frequency too low, you're going to have aliasing problem, so you lose some information. Okay? So based on that, you choose the sampling frequency very carefully. Now let's look at the quantization. The parameter, the important parameter in the quantization is the number of bits. When you look at the A to D is a chip. Okay? A to D converter is a chip. You can just Google it, and you can search on the website. Then you can find many different chips for A to D converter. And when you look at the specification of each chip, A to D converter chip, you'll see that this chip is 10-bit A to D or 8-bit A to D. So you're going to see how many bit for A to D. Okay? So let's say 4-bit A to D. Then what that basically means is the number of levels we have here 1, 2, 3, 4, 5, 6, 7, right? The number of levels is going to be 2 to the number of bits. So for example, let's say when you look at the one chip, right? And that chip is 4-bit ADC, okay? A to D converter, 4-bit. That basically means the number of levels in quantization for this chip is only 16 different levels. Okay? That's very cheap. Very, very cheap. What about 8-bit ADC? This one has 64 different levels, right? 64 different levels. So if you have more levels, like 64, okay, which one is better? This one is much better. Why? Think about this way. You have only 16 levels, right? In that case, what happens is you have a lot of errors. We call that as a quantization error because actual value, when you look at this one, right? Actual value probably is somewhere here. This is actual value, the real value. But based on the quantization, you cannot have this value. Okay, your output should be this one or this one. If this value is close to this, then your output is going to be this. If the actual value is close to this, then the output is this. So you will always have some error. That is a quantization error. But if you have only 16 different levels, then the gap between these, each level is really big, right? So you're going to have a lot of quantization error. But if you have more levels, so for example, if you have 16, if you have only 16 different levels, right? The actual value is here, but you cannot have this value. So your output is going to be this one or this one. So you're going to have some error. That's quantization error, right? But if you have 64 different levels, then you have more levels, right? Something like that. So your error will be reduced. So your quantization error is much, much reduced. Eventually, if you have more bits, let's say 16-bit ADC, let's say 12 bits, 12-bit ADC, then you have a 4K, right? 4K, 4,000 levels. So this is a very excellent ADC. Of course, very expensive, very cheap, expensive, but this is what we call as a high-end product, high-end. So when you look at the audio, right, audio, depending on which chip your audio system use, sometimes your audio use this kind of ADC, so that's very expensive audio device, audio system, high-end product. Some of them use a cheap one. That's like a source, that's just middle class. Kind of, right? Yeah. So generally, when you have a high number of bits, large number of bits, quantization error is much reduced. So generally, more number of bits, that's better, but much more complex and also expensive. So that's the issue. Okay. So remember that when you do a sampling, you need to choose a sampling frequency. When you do quantization, you need to choose how many bits you need, or how many levels you need for quantization, right? We have two different issues for these two. For the sampling, okay, as I said, the number one issue is to choose a sampling frequency. So we have some equation, but let me skip to this one. So there is a guideline for how to choose a sampling frequency, okay? the one guideline we know is Nyquist sampling theorem. Okay, what is the Nyquist sampling theorem? Yeah, so Nyquist sampling theorem tells you that when you look at the frequency of your original information, okay, your original information, original message, let's say our original message has a, this is a frequency domain. Our original message has this kind of frequency distribution, okay? So this is your frequency domain, and this is the frequency bandwidth, frequency information of your original signals. What you need to do is that you need to look at what is the maximum frequency in your signal. Okay, your signal has many different frequencies, right? But look at the maximum frequency of your signal. Let's call that as FM. Okay, then your sampling frequency, you need to choose the sampling frequency at least 2 times of your maximum frequency. So your sampling frequency should be higher or equal to 2 times of FM. That's your Nyquist sampling theorem, right? If you choose the sampling frequency lower than this, if you choose the double of that, then somewhere here, right? This is like 2 FM. So this is the sampling frequency. This is the lowest sampling frequency for your system in order to avoid aliasing. If you use lower sampling frequency than this one, somewhere here, then you're going to have an aliasing problem. But if you choose the higher than this one, if your sampling frequency is higher than 2 FM, then you don't have any aliasing problem. Okay, your information, you are not going to lose any information. But what's the problem? Complexity. Okay, you are doing sampling faster than enough. You need only this frequency, this sampling frequency, but you are doing much faster. So complexity is a little bit higher if you do that, right? So that's a Nyquist sampling theorem. So Nyquist sampling theorem or sampling theorem certainly is related to the aliasing problem, right? So what is the aliasing problem? So that's the one of the very important thing in DSP course. Okay. So let's see. When you have this signal, let's say this is your signal. Okay. As I said, this is your maximum frequency. Let's call that as FM. So your Nyquist sampling theorem tells you that 2 FM should be, or higher, should be your sampling frequency. But let's say I choose somewhere here as my sampling frequency. Okay? In that case, I'm doing undersampling. So this is a sampling required based on Nyquist sampling. So if you do oversampling, that means you are sampling much faster than enough. In that case, as I said, you're losing complexity. You are making your system more complex. But that's okay. I mean, complexity, you have a little bit complex system, but you don't lose any information. But if you are undersampling, okay, then the problem is you're going to lose some information. So let's see why that's the case. Okay, so the domain that we are looking at is analog frequency. F is analog frequency, right? Did you learn the digital frequency? There is a digital frequency concept, right? When you take a sampling, this is an analog domain. When you take a sampling, sampling is the number one procedure to change the analog to digital, right? So this is the analog signal. So you're going to look at this kind of frequency domain. Now you do a sampling and go to the digital domain. Okay, then our frequency domain now is going to be changed. And when you do sampling, that basically means that your signal basically repeats. Something like that, repeats, right? That's the digital. And from here to here, maybe here is FM, like 1 kilohertz or 2 kilohertz, something like that, right? But in digital frequency domain, you don't have kilohertz concept. This hertz concept is gone. Why? Because this is an original frequency. Now you apply the sampling to change the analog to digital. When you apply the sampling, this digital frequency is a normalized frequency. So original frequency divided by sampling frequency. You do a normalization, right? That's what you do. That's analog frequency, change it to the digital frequency. So you divide by sampling frequency. So the original frequency is like hertz, like 1 kilohertz. Sampling frequency is also like 2 kilohertz. So you cancel out. So digital frequency has no unit. Here in the digital domain, digital frequency domain, it's like from 0 to pi, minus pi. So you're going to see like a pi, 2 pi, something like that, right? So that's the digital frequency domain. This is the analog frequency domain. So whenever you see the digital signal processing, you are not going to see this one anymore. Okay? This is what you always see in DSP course. That's what you see, right? In DSP course. So that's the relationship. Okay? In this case, this is the digital frequency. So based on this, there's nothing like hertz. We don't use hertz because we are doing normalization. Okay? So you're always going to see this one. And then what happens is this repeats. Every 2 pi, you repeat. So this is what happened at the digital signals once you sample it. Okay? Once you sample it, it's going to change it to this. Now, when you sample it, the important thing is you need to choose a sampling frequency and then sample it. But if you do undersampling, let's say here, then what happens is the repetition happens based on this sampling frequency because this is the frequency you use to sample it. So therefore, what happened is that let's say if you use the 2FM, the exact NIQ sampling rate, then this one has FM. So if you use this 2FM as a sampling rate, then this one and this one meets like this, right? Because here is the sampling frequency you use, 2FM. But if you do undersampling like FS, that basically means you have this kind of thing. Here is FS. Do you see what I'm saying? So that's what happens. So here we have overlap. And this overlapping basically means that your high frequency component will go back to your own. It's like a ghost. It's my signals, but in my signal, I have some high frequency component. But since I use the undersampling, that kind of signal, that frequency, that's my frequency, but high frequency, that signal comes back to my own as a ghost. Okay, something like, for example, right? Let me look at it here. For example, here's a 1 kilohertz. So if you use sampling frequency as a 2 kilohertz, right, and then sampling, then it looks like this way, which is good. But if you use, let's say 1.5 kilohertz as your sampling frequency, in that case it's undersampling, what happens is, for this 1.5 kilohertz, you're going to have another image. We call this an image, right? You have image, every image in 2 pi. So therefore, what happens is, this signal here, which is 750 hertz to 1 kilohertz, this frequency will go into your signal. So this part was originally 500 hertz to 750 hertz. So your original information of this was frequency, and this frequency is added. Okay, your frequency, high frequency component will go back into your own signals, and everything is mixed. Okay, so that's what happened in aliasing. Once this happens, you cannot recover. There's no way you can correct this. you're going to lose information. It's completely wrong. There's no way that you can recover. That's why aliasing is a very bad one, and you need to avoid the aliasing problem. Anyway, so that's the aliasing problem. So the sampling frequency, you need to avoid the aliasing problem. To do that, a Nyquist sampling theorem suggests you to use the 2 times of your maximum frequency, okay, at least. Okay, we have some aliasing problem here. You can take a look at it. So this picture just illustrates. This is your original signal in frequency domain, and here is the bandwidth. If you choose a sampling frequency higher than 2 times of your maximum, then this is what happened in the digital domain. Okay? This is a digital domain, right? You see that this repeats every 2 pi, and that's what happened when you choose the right sampling frequency. However, if you do undersampling, this is what happened. It's like overlap. So once you overlap, you're not going to lose it. See here, you see here, originally your shape looks like going down like this, but because of the image, this one flips over and is added. That's why it goes up like this, because this part is added. Now you have a high value, something like this, right? You can never recover this. So that's aliasing. Okay, based on this, what we're going to discuss today is digital pulse modulation. Okay, from now and onwards, we're going to talk about digital modulations. Digital modulations. In analog modulation, remember that we have MT, our message signals, right? And then you multiply carrier, then you transmit it, right? That's your ST. That was our analog modulation. Simply amplitude modulation in this case, right? This is an amplitude modulation in analog, right? So this is what we call as a carrier. Okay? So we used sinusoidal carrier, sine, cosine type of thing, right? That was a carrier we used earlier in analog modulation, in analog. Now, in digital modulation, especially in pulse modulation, the carrier we use is not this one. Instead, we're going to use pulse carrier, like this. Okay, we're going to use this kind of pulse. We call that a pulse train, because pulse keep repeats, pulse train. We're going to use this pulse train as our carrier. Okay, once you multiply this pulse train into your message, now you're going to get pulse amplitude modulation. That's what we call pulse amplitude. So this pulse amplitude modulation is same, it's almost same as amplitude modulation in the previous analog amplitude modulation. Only difference is that this pulse amplitude modulation use pulse train as a carrier, not the cosine. That's only difference. That's PAM. Okay, then now let's see what happened. Let's say when your message, your original message, can go up and down, up, down, like this, right? That's your message, your MT, right? And this message is now multiplied with a pulse train. So what's going to be the output? Something like this. See that here we have some smooth curve, right? That's our message MT. Okay, this one is multiplied with a pulse train, like this. Then the output is going to be, let's see. So that our message, original message signal. Message signal is like this, right? That's our message signal. Now you multiply message into pulse train. What you're going to get is something like this, right? Something like this. So you still have the same envelope, but actual signal you have is pulse. But pulse, the amplitude is now changed based on MT. Okay? But the carrier looks like a pulse train. This one has the same equal amplitude because each one is the same pulse as a carrier. Okay? Multiply into your message, then your carrier now changes its own amplitude based on the message. So if the message goes up, your pulse goes up same way. Okay? That's the output of a pulse amplitude modulation. So in pulse modulation, okay, signal is always pulse. But this pulse amplitude modulation, now the information is in the amplitude. So therefore, if you have original message, depending on the original message, now you have a different amplitude in the pulse. But still it's a pulse. Okay, so that's a pulse amplitude modulation. Okay. Second thing is a pulse position modulation. Also pulse width modulation. There are three different modulations. PAM, this is a PAM, pulse amplitude modulation, and PPM, that's a pulse position modulation. Third one is a pulse PWM, pulse width modulation. So if you are if you're familiar with some microprocessor or something like that, you probably heard about PWM, right? Yeah, so this is the same thing, pulse width modulation. So let me tell you what that basically means. This is how to make a pulse width modulation. Okay, so let's say this is the red one is original message, MT. Based on the original message, MT, if the message goes up, now look at this is the output. Okay, your width, pulse width is now getting, the pulse is getting fat, right? The width is large, yeah, getting wider and wider. Now the MT, original message goes down, then it's getting narrow. Okay, the pulse is getting narrow. So that's a pulse width modulation. So depending on the width of the pulse, okay, you have a different information. So that's a pulse width modulation. This picture shows you also the pulse position modulation. This is our original message MT as an example. Okay, and this is a pulse carrier. Pulse carrier, this one, pulse carrier. This is a pulse carrier. So when you multiply this pulse carrier into your message, now you're going to get the pulse amplitude modulation, something like that, right? That's a pulse amplitude modulation. But when you do pulse width modulation, what happens is when you have a message high value, large value, your pulse is getting fat. When your message goes low, pulse width is going to go slim, like narrow, right? That's a pulse width modulation. The last thing is a pulse position modulation. Pulse position modulation is like original pulse this is the original pulse train, looks like. And when you do the pulse position modulation, what that basically means is each pulse now is in a different position. Let's say your original MT, your message goes up and goes down. When the message goes up, now the position of the pulse is getting delayed, large delay. And when the message goes low, okay, message value goes low, the pulse will be delayed only a little bit. Okay, so how much delay you're going to have, that depends on the message, and that makes your pulse position. Okay, if you get a maximum value, this position will go all the way here. Okay, now then, something like this. So this delay, that actually allows you the position. So how to make that is, look at here. It's very simple actually. This is a pulse width modulation. Right? You have, when the original message has a high value, your pulse is getting fat. But here the starting, this rising edge is always at the right position. Okay, see here, this is a rising edge. Same as here. This is the original pulse carrier. Same here, rising edge is always same, right? In pulse width modulation, rising edge is always same. Only the falling edge here, falling edge is different depending on your message. If the message goes up, now falling edge is a little bit delayed because the width is large, because the pulse needs to be fat. Okay, so this falling edge are now in a different position. That's what happened in the pulse width modulation, right? So every time that this pulse width modulation has a falling edge, at that position, you're going to have rising edge in ppm. Okay? So look at here. This falling edge and rising edge same at same time. This falling edge, this rising edge at the same time. So every time when you have a falling edge in PWM, you're going to have a rising edge of ppm. When you do that, okay, now in PWM, the falling edge have a different delay. This one is a large delay, right? Even large. This one is a very small delay. So because of that, your pulse are positioned in different way. Okay, pulses are located in different position. So that's a ppm. Okay, so just compare with this pulse modulation with analog modulation we learned. PAM, like this one. This one is almost the same as amplitude modulation in analog. It's almost same, right? Even the name is almost the same. Amplitude modulation, this is a pulse amplitude modulation, exactly same because your information is in the amplitude. In this case, a pulse amplitude, right? Your amplitude has information. The only difference is that in the analog AM, we use a sinusoidal carrier. This one, we use the pulse train as a carrier. Okay? Only the carrier is different. Everything is the same. Now, look at here. What's this one? PWM. This one, amplitude is not going to be changed. Amplitude is always the same, right? Amplitude is same. The only difference is that this pulse width now changes. Sometimes fat, sometimes narrow. That is what is changing, depending on the information, right? So this one almost the same as FM. I mean, somehow, right? In the analog FM, what happened? In the analog FM, the amplitude is always the same, right? Depending on your message, sometimes you have a low frequency, sometimes you have a high frequency. That's what happened in the FM, right? This one looks almost similar. Okay, amplitude is always same. Depending on the message, sometimes the pulse becomes fat, sometimes narrow. That's PWM. And ppm is actually same pulse, same size of pulse every time, but it is located at different position. Sometimes with a large delay, sometimes a small delay, something like that. That's a pulse position modulation. Generally, microprocessor, a lot of chips, a lot of hardware, a lot of peripherals, they use a PWM to do motor control, to do like many different things, right? They use a PWM signal like this. Okay. So why are we talking about pulse modulation, by the way? We are talking about PAM, PPM, PWM. All of these is a pulse modulation. What's the difference between pulse modulation and the analog modulation we learned before? Carrier, yeah, of course its difference is carrier. But in amplitude modulation, we learned before, that uses the sinusoidal wave as a carrier. But this pulse modulation uses the pulse train as a carrier. Why we use a pulse train in this case? In what's the scenario? Okay. Simply speaking, right? If you use analog modulation, like AM, FM, those things, we're gonna send the signal over the air. In the air, sinusoidal carrier is the best carrier. Okay, most efficient carrier. If you use a pulse carrier like this and transmit over the air, you cannot transmit. Okay, you cannot transmit. Why is that? Because this kind of pulse train has an infinite frequency. See this rectangular, right? In frequency, it's going to be sync function. You have all the frequency. You cannot transmit. So sinusoidal carrier is the best one over the air. But this PAM, pulse modulation, is not to transmit over the air. Then where do you use this? Circuits. Okay, circuits on the circuit, like a PCB, right? Chip-to-chip communication. You know, there's a one chip, microprocessor. There's another chip, motor control chip, for example, right? So you need to do communication between these two chips. For something like that, the voltage or some chip, hardware, right, between the chips. And in those kind of channel, not the wireless, not over the air, but between the chip, right, in the voltage, in that case you use a PAM or PPM, like a pulse modulation. So in those kind of channel, this one is okay. Okay, so in those areas you use this pulse modulation. Okay, as you mentioned earlier, we have a quantization process, right? Simply the quantization is like if your original value is between a certain range, like your value is between the mk and mk plus 1, right? Then you're going to get a representative value. So that's the quantization. So that's what we call this amplitude quantization. So simply speaking, we have a quantizer. This is a block diagram for quantization. You have input signal. Input is analog. We have a quantizer block, and we have a G. G is a function for quantization. And the output is going to be discrete value. So input is a continuous value into the quantizer. Output of the quantizer is going to be discrete value. Okay, so that's output. Let's see what this quantizer function looks like. G is a quantizer function. So we typically think about two different quantizer functions. So these are same thing. Okay, same thing. It's like a staircase function, right? So this is a quantizer function looks like. See here is the input, x-axis, y-axis is output. So how to read this is that let's say your input. Let's take a look at this one. Same thing, actually, both are same, but let's take a look at this one. Let's say our input is 0.5. Okay, if our input is a 0.5, it's somewhere here, right? Then what's going to be the output? Output is this value. What about 0.6? Still same value. 0.9, still same value. Okay, your output is still same. What about your input is 1.1? In that case, 1.1, you're going to get another output, but suddenly jump, right? So you can never have an output value between these two, because see here, the mapping is between here to here, you get this output. Between here to here, you get this output. Something like that, right? That's quantizer function, right? So that's why we have a staircase function like this. So that's what quantizer works. Okay. So we have two different ways, but it's basically the same thing. That's what quantizer. So generally, the quantization is like a unit step. The uniform quantization. See here, we have a range between here to here. If the input is between here to here, you get this output, right? Here to here, this output. But look at the range. This range, this range, this range. These are all same range. And also the output value, this is all with the same step size. This is called the step size. We have a same step size every time. So look at, this is a stair step. It's the same, right? Same all the time. So that's what we call uniform quantization. Okay? That's typically what happens for quantization. That's the pulse modulation. Now we have another modulation called the pulse code modulation. This pulse code modulation certainly is related to the pulse modulation, but this is a pulse code modulation. Simply speaking, this pulse code modulation is used for typically audio signals. And what to do is that inside the pulse code modulation, we are typically using the non-uniform quantization. So I'll tell you what this non-uniform quantization means. Okay? Let's say we're going to use this quantization. Okay? Say we have input, message, let's say. We have a quantization here, and let's say we have output. Let's think about this scenario. Okay, you have input signals which is analog. You have analog signal comes into the quantizer, and you're going to get the output. But output is a discrete value. But what this quantizer looks like is this one, right? So you see that this is an input-output relationship, and you have your input-output relationship, something like this. Okay, so that's your quantizer. And now the maximum output value, let's say, is a 5 volts. And the minimum output voltage is a -5. Okay, let's say that's the case. Okay, now what is happening is this quantization, uniform quantization, is sometimes good, but in a lot of cases, this kind of uniform quantization is not very good, because think about now MT. This MT, our input signal, is analog signal, something like this, right? Sometimes. If your analog signals have a maximum value of, let's say here 5 volts, same way, -5. If your input signal has a maximum 5 volts and minimum -5 volts, but inside here you have a same here -5, here +5. You have a similar distribution like this. You have similar distribution like this. Then this uniform quantization works very good. So what I'm trying to say is, this is your input signal, right? Think about two different signals. This is one signal, one type of signal. Another type of signal is, again here 5, -5, but another type is something like this, right? Okay. So let's compare these two different signals. The first signal is fully using all this direction, all this range. Okay, so maximum is 5 and minimum is -5. Same here, maximum 5, minimum -5. But in this second case, what happens is when you measure the signal for a long time, most of the time the signal is very small. Only, okay, most of the time the signal is very small. Only when sometime you get a peak into max or mean, and then most of the time you get a very small signal. That's the signal, second signal. First signal is you are gonna swing fully. So that's another signal, right? This kind of signal, when you look at the distribution, the value distribution, with some high probability you get this value. With some high probability we get this value. Also high probability with this small value. But in this case, if you look at the distribution, this one happens maybe once in a while. This one happens once in a while, but most of the time this happens. So when you draw the distribution, it's going to be like this, right? The distribution is going to be like this. Most of the time you have this value. So with the probabilistic sense, most of the probability goes into here. Do you see the difference? So this kind of uniform quantizer works best in this kind of scenario, for this kind of signal. Why is that? Let's say we have this quantizer, uniform quantizer, but our input looks like this. In that case, what happened? Most of the time you have very small signals, like 0.5, minus 0.2, something like that, right? Very small signal. In that case, this is the input, right? 0.5 to minus 0.2, somewhere here, somewhere here. So most of the time you have here input, right? Sometimes input is a 0.5, sometimes minus 0.5. So your signal, input signal is somewhere here, very small amplitude. Your input is somewhere here. So therefore your output always is going to be this one. You get the same output all the time, most of the time. Only when you have a high value, once in a while, then you get some value here or there, right? But most of the time you get this value. However, this one, in this case, your signal swings like that with a wide range. So sometimes you get here, sometimes you get here, sometimes here, 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 like with equal probability. Okay? Now, think about our signal. Let's say our voice. Our voice signal is more like this one. Okay? And there are also other signals which more like this. So when you have this kind of signal, our quantizer, uniform quantizer, give you very, very bad performance. So what would be the best quantizer for this one? The best quantizer for this one, ideally speaking, the best one is non-uniform quantization. Okay, generally. So non-uniform means that this one you have a same size, right? Same size of steps every time. But non-uniform equalization means that sometimes you have a small steps, sometimes you have a large step. That's non-uniform quantization. Okay. So then, let me ask you a question. I'm going to draw the non-uniform quantization. This is one non-uniform. So you have a small steps in here, in the middle. You have a big steps on the side. Second thing is the opposite. You have a small size of small steps, and in the middle you have a big steps, small step here. Which one works better for this one? Huh? This one works best. This one, right? Why is that? Because most of the time your signal is very small. So most of the time your signal is right here, right? So by making step size very small here, okay, in here you make a very small steps. That way you can reduce the quantization error. Okay, when you make a step size small, always the quantization error is very small. Okay, but that's what happens most of the time. So that's why you want to make a very small steps in here. That way you're gonna have a small quantization error, but here and here you're gonna have a very big steps, right? So here you're gonna have a very large quantization error. But that's okay because we don't have that much, right? We have that only once in a while, so that's okay. So that's the concept of non-quantization. Okay, for this kind of signal, we need to have non-uniform quantization. That's what is the best case. Now the problem is that this kind of non-uniform quantization, it's very difficult to make in hardware. We cannot make this in hardware. Okay, very difficult. So hardware always use this quantization, uniform. This one, it's very difficult to make. So how do you do that then? So that's why we still want to use this uniform quantization because it's very difficult to make this one, right? So we want to use the uniform quantization, but we want to try to make this kind of thing. So that's why what we want to do is, this is our input. Okay? We are trying to make this input to this one inside the hardware, inside the coding. So that's what we call as a pulse code modulation, PCM. So this is our original input. Okay? For this original input, we are kind of making into this way, and then put it into the uniform quantization. That's what we are trying to do in this PCM. Okay? So we are not actually making the non-uniform quantization hardware. The hardware is uniform quantization, but we are trying to mimicking, pretending to use the non-uniform quantization. So that's what happened. To do that, what we need to do is we need to do this compression. We call it as a compressor. And this equation here and this equation, this is called the mu law, this is A law, but this is a simple equation, how to do compressing. And let me tell you what that means by graph here. This is a compression, see compression laws, right? This is a mu law, this is A law. But this graph looks like a log, right? Log function. This one is how to change this signal into that one. So in this signal, in order to convert this kind of signal to this way, what do you need to do? Simply speaking, right? Small signals, you're going to multiply big number. So you're going to make it bigger. So this small signal, you are multiplying large gain. That way you are making bigger. This big one, you are already big. So you are multiplying a little bit small value. So you are increasing a little bit small value. So that way, this one, let's say our input signal is something like this. Okay? This is our input signal. Now in this input signal, you are multiplying this input-output relationship, like a linear, like this linear input-output relationship. Then the output is going to be same, right? Of course, the output is same as this, because this is linear. However, if I multiply log kind of graph with that, okay, what that basically means is if my input signal is small, I make it bigger. If my input is big, then I get this value. So in the input, let's think about two input samples. One sample has this value, another sample has this value in the input. In the input signal, these two different sample, you have this big difference, but at the output, you have only this much difference. So therefore, when you put this signal into here, now your output is like that. So see here, this part is now bigger. But this part almost still same size. Do you see what I'm saying? So that's what happened here. That's why you see this log function. When the input has a sample 0.2, let's say, your input is very small and 0.2. The output is going to be 0.65. So the output is going to be bigger. If your input is 0.8, okay, then based on this, your output is like a 0.9. So it's a little bit increased. But that's what this compression law works. That's how this graph looks like. Okay? And based on this mu parameter, now you can change how much you want to amplify. If you use a mu equal to 0, that means it's going to be linear, which means your input just go to output, same way. But if you have a large number of mu, that means you are amplifying the small value much large. You are amplifying the large value a little bit. So that way, this kind of signal now changes into that signal. Okay, so that's a PCM. There's another modulation called the delta modulation. And what is the delta? Delta means difference. There's one sample, there's another sample. The difference between two samples, that's delta. So this delta modulation is to calculate the delta or calculate the difference between two samples, two consecutive samples, and then accumulate that. That's delta modulation. So let me tell you on the graph here. So this is the original information, original message. Your smooth curve, right? That's original message, MT. Now when you use this smooth curve as the input to the delta modulation, the output looks like a staircase function. That's the output of delta modulation. So in this delta modulation, the output is only one bit, up, down. Okay, up or down, only one bit. So let's say we start from here. How to do that is your original signal, input signal goes up, right? So on the next sample, what we're going to do is we're going to choose up. So it goes up. Okay? And then on the next sample point, now you're going to compare this original signal and then your current DM modulation and compare these two. And if this one goes up, then you can still go up. Otherwise, you can go down. So in this case, go down. And right here, your input signal goes up. So therefore, your DM output is going to go up, up, up. Try to catch. Your DM output is try to catch the original signal. So that's the DM, delta modulation. So you are just think about the delta, right? Think about the delta. Right now I'm here, but my original signal goes this way. Okay? Then let's try to catch it by my putting the delta onto the same direction. Goes up, 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 like that. And if the original slope, original message goes down, then I have to try to go down and down, down. Try to follow, right? That's what delta modulation. But look at here, this gap, sample gap is always the same. And also the step size is always same. That's already fixed. Step size is already fixed. And this one, sample duration, is also fixed. This is called the TS. TS is sample duration. And the step size, delta, this delta is also fixed. Okay, that's fixed. So that's a delta modulation. And based on that, if you look at the output, what's going to be the output? Input is this message. So this smooth curve is going to be input to the delta modulation. What is the output of delta modulation? This one, 1 0 1 1 1 1 0 1 0 0. That's the output of delta modulation. So what does that mean? 1 means up, 0 means down. So just compare this bit sequence with your this graph. 1 means up, 0 means down, and here 1, 1, 1, 1, right? So 1, 1, 1, 1, something like this, right? So that's going to be the output of your DM modulation. So eventually the analog signal is now converted into the bit sequence like that. That's the DM modulation. Okay, so that's some of the equations. So at the receiver, in the DM modulation, that's how to change the analog signal into digital in DM modulation, and that's a signal we transmit. And at the receiver, what you need to do is you need to get this bit sequence, and you should be able to recover this one. You should be able to convert this bit sequence into the analog signals, right? So how do you change this digital bit sequence into the analog signals? How to do that is the same one, right? 1 means up, 0 means down. And what you need to do is you need to accumulate. 1, 0, 1 means go up, 0 means go down, and 1 means go up, and again from that up, you need to accumulate. Okay, you need to accumulate. It's not like 1 and starting from 0 again up, from 0 again up. It's not like this, right? You are doing up, you accumulate. That's why you need to have a sigma here. You have a sigma accumulator. At the receiver, you are keep accumulating the receiver. Okay, so that's what delta modulation look like. In this delta modulation, we generally have two problems. One is called as a slope overhead distortion, and second is a granular noise problem. Okay, so here's what happened. Let's say this is our original signals, input signals. But when you take a DM modulation, if you use the sampling too slow, okay, if you're sampling too slow, then you cannot catch it because you are trying best to catch, but this one goes too quickly, goes up too quickly, but you have your own sampling frequency, so you can only catch. This is the maximum you can do. This is the best you can do to catch. So in that case, you see this colored region, right? This colored region is error. So this is a big error, right? So that's the slope overhead distortion. Your slope is too fast. Okay, that's what it means. Second error is the granular noise. When the original signal is almost flat, then in DM modulation, there's no flat. You need to go up or down. So what happens is you need to go up, down, up, down, up, down. That's what you do, especially for flat signal. So for every time when you go up, you have a little bit of noise here. Okay, that's an error component. And this error is because of your step size. If your step size is small, then this error is much reduced. And this slope overhead problem is because of your sampling frequency. If you have a fast sampling frequency, then you can catch fast, right? But the sampling frequency is too slow. So that's why it goes up slow like this. But original signal goes up very fast. So this problem is because of sampling frequency. This problem is because of quantization. So you need to design your DM modulator to choose the sampling frequency and quantization in order to avoid these two problems. Okay? That's the common problem for those modulations. And delta sigma modulation is actually same as a delta modulation, but the only difference is that in delta modulation, the transmitter is simple. You just go up or down, and make a 0-1 sequence and transmit. And receiver, you basically accumulate and then recover. But in delta sigma modulation, what you do is this accumulator in the receiver is now moving to the transmitter. So transmitter has accumulator. The benefit is, in this case, the receiver is simple. So that's the delta sigma modulation. So yeah, that's the only difference between delta modulation and delta sigma modulation. Okay, so this is the last thing in this slide. So line coding is a simple coding to for pulse, right? Pulse coding for line. So typically we can consider many different one, but each one is used for different purpose. Typically on-off keying, we call this on-off signaling, but sometimes we call this on-off keying. On-off keying is a simple one, right? When you have a 1, you have on. When you have 0, off. But this one, on-off keying typically has some problem, right? And NRZ as well, this one has some problem. The problem is, if you have a 1, 1, 1, 1, 1, 1 sequence, you have always on. But if you have a 0, 0, 0 sequence, you have always 0. So typically, when you have all 1s or all 0, then it's very difficult to recover the clock. Okay? And also, typically, it's always better to have a transition, 1, 0, 1, 0 transition. That's much better for clock, recovering clock. That's why in a lot of cases, this kind of thing, Manchester code kind of thing is always, it's preferred, right? In Manchester coding, it's like going 0 and 1 every time, right? Because you change original 0 into low to high and 1 into high to low, something like that, right? So every time 0 or 1, even you have a 1, 1, 1, 1, 1, still the 0, 1, high, low is a transit, always, right? In Manchester coding. So that's for line coding.